Hello students, in this video we'll discuss what it means for a family of vectors to be parallel along a curve along a manifold. So if we're given a curve, t goes to x1 of t, xn of t on a manifold or a surface, then we say that the family AI is parallel or parallel transported along this curve if the intrinsic derivative of that vector is equal to 0. Now recall what this intrinsic derivative is, right? So this intrinsic derivative, recall, the intrinsic derivative of a covariant collection AI is going to be what? Is going to be the covariant derivative of AI hit with dxm dt, right? Which we saw was exactly equal to what for a covariant vector? For a covariant vector, this was dai dt, and then plus gamma, and then an im, and plus gamma im for the covariant thing over here, we have to put upstairs, right? And so we're going to have a gamma and then a dx, dxm dt. So we're going to have an m up here, we have an m up top, we have an m on the bottom to trace that thing over there, and then we're going to have a l over here, an I on top, and then a l, and then a dxm, like that, of t. Okay. So in other words, if this expression over here vanishes, then we say it's parallel, right? So equals 0 implies parallel to the curve. Okay, great. All right, and of course, same thing is true for contravariant vectors if we have a minus sign over here. So what are some of the basic properties of these things? So let's recall, so suppose, here's a proposition, okay? We claim that this family over here, dxi dt, is parallel along geodesics of the curve. Along geodesics, okay? So in other words, if I have a curve, right, and that's a geodesic, then the tangent vector is parallel along the geodesic, right? So tangent vectors are parallel along geodesics. Okay, great, and so let's recall what the geodesic equations are. So the proof, recall the geodesic equations are d squared xi dt squared, and then plus gamma I j k dxj dt dxk dt is equal to 0, right? And so now let's compute this derivative over here. So if I did delta t of this vector over here, dxi dt, that would be the second derivative of dxi with respect to t squared. It's contravariant, so the gamma goes upstairs, and then I need two parameters over here, so a, b, and then what we have over here, we're going to have a what? We're going to have a dxi dxa dt, and then a db dt, right? For the other parameter of this index over here, so dxb dt. But those are exactly the geodesic equations, so this expression is equal to 0. Great. All right, so that's the first example. That's our prototypical example of parallelism, right? If I give you a geodesic and a manifold, I automatically know the tangent vector to that curve is going to be parallel transported along that geodesic. Okay, great. And so now there's two other properties we want to prove with geodesics. So let's recall that for a vector A, so if A is a contravariant vector, then what do we say about the length of A squared? Then the length of A squared is by definition Gij Ai Aj, and this is an invariant. Okay, And let's suppose, so since it's an invariant, its intrinsic derivative is its derivative. So for invariance, we know that d by dt, the total derivative, is equal to the intrinsic derivative, okay? So now, if I do the derivative of this thing over here, so let's take this equation over here and differentiate it, right? So if I had d by dt of the length of a squared is the same thing as d by dt of this thing over here, d by dt of gij, and then aij. But that's the same thing as the intrinsic derivative of this thing. And now let's use the product rule, and know the fact that the intrinsic derivative of gij is equal to 0 because the covariant derivative is equal to 0. So this is going to be 2 gij, and then times one of these things over here. So times d by dai, delta a of t, and then aj. And that is equal to 0 if a is parallel transported, right? So if a is parallel transported. To the curve. Okay, so if we assume that a is parallel to the curve, what does that say about this thing over here? Well, of course, what is this? This is really just nothing more than just 2 times the length of a times d by dt of the length of a, like that. And so that tells me that d by dt of the length of a is equal to 0, so that says that a has constant length. So ai has constant length if it's parallel transported. It's constant length. And by the same reasoning over here, if you have two parallel transported vectors, the angle between them by the exact same argument, because all I'm going to do if I do parallel transport of two vectors, I'll place this ai with a bj, and I know that if bj and ai are parallel transported, then the angle between them has to be constant by the same exact calculation over here. So for parallel transport of a contravariant vector along a curve, it must have the same length as it is parallel transported along the curve. If I have two vectors that are parallel transported along a curve, they have to have the same angle as they're parallel transported. So in further videos, we'll see the connection with this and the idea of the covariant derivative connection with the Lie derivative along a curve. And so we'll see that these ideas coincide when we start to go more advanced and do our study of Riemannian geometry. Thank you very much.